Hey there, have you ever looked at an app on your phone and just wondered how it all works? Like, how does a simple idea turn into a real working program? Well, today we're going to pull back the curtain and walk through that entire recipe from a basic problem all the way to code a computer can actually run. Let's get into it.
So it really boils down to this one big question, right? How do you tell a computer exactly what to do? I mean, these machines are incredibly powerful, but they're also super literal. They will do precisely what you tell them, which is great when you're right and not so great when you're not. So the whole challenge is giving them instructions that are perfectly crystal clear.
And here's the secret, the thing most people don't realize. Programming, it's not really about the computer, at least not at first. At its heart, it's all about a very human skill, just having a structured way to solve problems.
And before we even think about writing a line of code, we follow this universal process. What's so cool about this is that these 6 steps, they apply to pretty much anything in life, not just coding. You start by figuring out what the problem actually is. Then you brainstorm a bunch of ways to fix it, you weigh your options, and you pick the best one. It's only then that you start building or implementing the solution. And this is crucial. You have to look back at the end and ask, did it actually work?
Okay, so let's say we've decided on a solution. We can't just jump in and start mashing the keyboard. That's a recipe for disaster. No, we need a plan. We need a blueprint that maps out the logic before we get lost in all the little details of a specific programming language.
And that blueprint, it starts with something called an algorithm. Now, I know that word can sound a little intimidating, but don't let it fool you. An algorithm is just a recipe. Seriously, that's it. It's just a simple, step-by-step set of instructions written in plain English that tells you how to solve one specific problem.
This is a perfect way to see it in action. On the left, you've got a super simple algorithm for making tea. You know, step 1, get the stuff. Step 2, boil the water. It's just a list. But on the right, you see the exact same process laid out as a flowchart. Now, each one of those shapes has a specific job. One's for input, another's for a process, another's for a decision. It gives our simple recipe a really clear visual structure.
But, what if you need something that's a bit more structured than a simple list, but maybe not as formal as a big flowchart? Well, you need a bridge to get from that plain English plan into the world of actual code. And that bridge has a great name, Pseudocode. It literally means fake code, and it is the perfect middle ground for our plan.
And here's our tea-making example one more time, but now it's written in pseudocode. See how it's starting to look a little more like code? It's using keywords like begin and get, and the steps feel more like commands. It's still totally readable for a person, but it forces us to organize our thoughts in a way that's much, much closer to how a real program actually works. All right, so now we have our perfect blueprint, but there's a huge problem. A computer can't read our algorithm. It can't understand our flowchart. It has no idea what pseudocode is. We have to translate our plan into a language that the machine's processor can actually understand. We start at the very top with what are called high-level languages. You've probably heard of these, things like Python or C++ or JavaScript. They're called high-level because they're way up here, close to us humans. They use words and grammar that are pretty easy for us to write and understand.
Okay, now let's take a step down the ladder. Here we get to assembly language. This is way closer to the actual hardware. Instead of English-like words, it uses these short little abbreviations called mnemonics, and each one corresponds directly to one of the processor's most basic tasks. It's a lot harder for us to read, but it's getting much closer to what the machine is really doing.
And finally, we hit rock bottom, the foundation of it all, machine language. This is the computer's native tongue, and it's nothing but ones and zeros. That's it, binary code. Every single thing you want the computer to do, no matter how complicated it looks in Python, eventually gets broken down into these simple on or off signals for the processor.
So, that's the big question, isn't it? How do we get from our human-friendly code all the way down to those ones and zeros? We're definitely not going to do it by hand. We need some special programs that act as our translators.
And the 2 main types of translators you'll run into are compilers and interpreters.
Think of it this way. A compiler is like a book translator. It takes your entire program, the whole book, reads it all at once, translates the whole thing into a runnable file, and then, at the very end, hands you back a list of all the typos it found. An interpreter, though, is more like a live translator at a conference. It reads your code one line at a time, translates it, and runs it immediately. And the second it hits a mistake, it stops right there and tells you exactly where you went wrong.
All right, theory's great, but let's put it all together. We're going to combine all these pieces and look at the actual practical steps of how a program gets built, how it runs, and what happens when, things don't go perfectly.
So if we take the C language, for example, the whole process is pretty simple. First, you write your code in a plain text file, your source file. Second, you feed that file to a compiler, which translates it into a machine code file that the computer can actually execute. And third, you just tell the computer to run that new program. That's it.
But let's be real. Code is almost never perfect on the first try. So what happens when our translator finds a problem? Well, it's really important to understand the two main kinds of errors every programmer runs into.
Okay, check out this simple line of code. At a quick glance, it looks totally fine, right? But it's missing one tiny, crucial thing at the very end, a semicolon. And in a language like C, that's like writing a sentence and forgetting to put a period at the end.
This is what we call a syntax error. You've basically broken the grammar rules of the programming language. The compiler, our super strict translator, is going to catch this right away. It won't even try to build the program. It'll just stop and tell you, hey, you made a mistake on this line.
Now have a look at this example. The syntax here is perfect. Every semicolon is exactly where it should be. The grammar is correct. But the logic is totally broken. The program is trying to divide a number by 0, which, as we know, is a mathematical impossibility. And this is the much sneakier and often more frustrating logical error. The program will compile just fine, it'll run, but it'll either crash halfway through or it'll give you a completely wrong answer. In this case, your instructions were grammatically perfect, but the instructions themselves were wrong. The computer did exactly what you told it to do, it's just that what you told it to do didn't make any sense.
And there you have it. From figuring out the problem to drawing up a blueprint, translating it for the machine, and then fixing the inevitable mistakes. That really is the fundamental recipe for creating code. So now you know the steps, you have the map. The only question left is, what problem are you going to solve first?